Okay, cache replacement policies. Least recently used is a good strategy for cache replacement, and in a set associative cache, it's reasonably cheap to implement. When I say reasonably cheap, I mean, well, let's compare it with what happens on page replacement. Now, if you've studied operating systems, you may know that most OSs don't use strictly LRU page replacement, because there are just too many pages. You can't determine which one is the very least recently used. Instead, they use an approximation to LRU. But with a set associative cache, when a block needs to be replaced, we don't need to examine all the blocks in the cache. We only need to replace a block within a particular set. So we only need to determine which of the blocks in the set is the least recently used. And since there are likely to be no more than 8 blocks in the set, that's a much more tractable problem. Now, with an LRU algorithm, we can arrange the lines of the set in an LRU stack. So let's suppose we have this string of references, A, B, C, D, A, B, E, etc., and there are 4 lines. Then the LRU stacks after each reference are shown below. They're arranged in order of recency of access so that the most recently referenced is at the top and the least recently referenced is at the bottom. Here's a trace of accesses to these 5 pages, and the 5 pages are numbered A, B, C, D, and E, and so you should consider each one of those as being a page. Well, actually, consider each one as being a block because we're talking about cache replacement now. So there's 5 blocks, A, B, C, D, and E, but there's only room for 4 of them in the set. So first we reference block A, and it becomes the most recently used. Then we reference block B, and then A is the second most recently used, with B being the most recently used. When we reference block C, then it's the most recently used, with B and A being below it. And then we reference line D, and then A drops all the way down to the bottom of the set, with C and B being, second and third most recently referenced. And now we're going to reference A again. So this merely rearranges the blocks because we have the same blocks in the set that we did before, but A is now most recently referenced, D is second most recently referenced, and B is the least recently referenced. So now we're going to reference block B, and then it goes to the top and A, D, and C drop down. So every block in the stack has moved down by 1 except for the block that was referenced, and it has come to the top. Now, when we access block E, E isn't in the set, so it's going to replace something. So it's got to come into the set and replace something. And what is it going to replace but the least recently used block, or C? So now E is the most recently used, with B being next, A is third, and then D is last. Again, all blocks drop down by 1, except for the one that was just referenced, which is E. Now A is referenced, and A was at position 3, so it comes up to position 1, and E and B drop down. But D stays at position 4 because it's still the least recently referenced. Now we reference B, and B comes up to the top with A and E dropping down, and D still stays where it is. But now we reference C, and C isn't in the cache, so that causes a cache miss, and B, A, and E drop down by 1. And then we reference D and E, and they cause cache misses too, with the other blocks dropping down by 1. Well, how are we going to implement LRU in a set? The book tells us about 2 implementations. First is a matrix implementation, and second is PseudoLru. The matrix implementation implements LRU exactly, and the PseudoLru is, well, a pseudo-LRU strategy. It's based on a tree that's pretty similar to LRU, but it doesn't always necessarily replace the same line that LRU would. So let's look at the matrix first. We have block A located in way 0 of the set, B in way 1, C in way 2, and D in way 3. And then the access order of the blocks is B, C, A, and D. The matrix is initialized to all zeros. Every time a block is accessed, the row corresponding to the way is set to all ones, and then the column corresponding to the same way is set to all zeros. First to be accessed is B, so this means that way 1, it has its row set to 1, its column set to 0. Next to be accessed is row C, or is block C, so its row is set to 1 right there, and its column is set to 0. And then A is accessed, so the first row is set to all ones, the first column is set to all zeros, and then lastly D is referenced, and this causes row D to be set to all ones, and column D, or column for way 3, to be set to all zeros. And so now we can read out the results. And notice that the one that's got the highest binary number, 1110, is the one that's the most recently referenced. Next most recently referenced is the next highest binary number, which is 0110, corresponding to way 0, or block A. And then after that, way 2, or block C. And then finally, the least recently referenced block is way 1, which is where B resides. Now let's look at the pseudo-LRU tree approach. In this example, we're going to assume that we have a 4-way set associative cache with block A and way 0, B and way 1, and so forth. And our access stream again is BCAD, but then we follow it up with an E, which is going to cause a replacement. We start out with our LRU tree having all zeros at the bits, like you see right there. And the rule is that when we're accessing a block, if we have to move left to get to the block, then we set the bit to a 0 that we just traversed, and if we have to move right, then we set the bit to a 1. So when we access B, we have to move left at first, and so we set that bit to a 0. We move right at the second level, and so we set that bit to a 1. Then when we access C, we move right at the first level, so we set that bit to a 1, and then left at the second level, so we set that bit to a 0. When we reference A, we have 2 zeros because we move left and left, and when we reference D, we have 2 1s because we move right and right. Now we reference E, and we have to replace a block. So we read the blocks actually in the reverse sense that we did from the way we set them. So a 1 means to go to the left, and a 0 means we go to the right. This gets us to block B, okay? So a 1 there means we go to the left, 0 gets to go to the right. We get to block B, which was indeed the least recently used block. Then when we access E, the block that we just replaced B with, we have to move left to get to it and then right. So we set the bits to 0 and 1 like we did before. Now notice that in this case, the replacement was exactly the same in the pseudo-LRU tree as it was in the LRU matrix. But that needn't always be the case because this is an LRU approximation. Most of the time it will be the way things work out, but not always. So now to finish off, I'd like you to ask how many bits per set are required to keep track of LRU status in both of these implementations.